welcome to the GraceCUD Thursdays. GraceCUD Thursdays is a series of webinars we organize every Thursday at 10 on various HPC topics, such as this one today on Sycl, which will be presented by David Chamont from IJCLab, who will be introduced later on. But first, let me give you a little presentation of the organization team. There is Pierre Aubert, research engineer from the lab. It's a French laboratory of physics and particles in Annecy, in the French mountains. And Karim Azoum and I from Terratech, within the French NCC called CCFR. And with the lab of Annecy, we co-organize the GraceCUD Thursdays and the GraceCUD School. Because those 17 GraceCUD Thursdays you will discover are held by 9 incredible teachers who will each one of them give you webinars on their topics, introducing at the same time the program of the summer school. So what is GraceCUD School? It's a free summer school dedicated on programming and optimization on heterogeneous architecture. It was created 2 years ago by Pierre Aubert with a few people in Annecy. And we, the French NCC, joined him last year to help him develop it not only in Annecy, but also in 12 satellite sites among 4 countries. Those satellite sites helped us reach more people by broadcasting the school live in their locations. So the summer school had a 2-week program, 1 week on CPU and 1 on GPU. But everybody was free to choose the courses they wanted to attend, thanks to our à la carte option. And we finally trained over 500 people, and everything is available still on replays on our website and YouTube channel. So you can access it if you want, but obviously everything is in French. Luckily, this year we are going European, so all will be in English, like this webinar. You have various ways to attend the school, as you'll see in the video I'm going to launch for you. And also, we invite you to be part of the team and become a satellite site yourself if you want to host the school at your place. We are able to provide you everything, all courses, containers, access to the teachers, and also to connect you with our growing HPC community. So let me now play for you the video and present you the GraceCUD School 2025.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to GraceCUD School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or à la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Sycl, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, QPy, CU-numeric, JAX libraries, and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G Fortran, and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Nsight, Malt, and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together, and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
So if you have any question regarding the school, you can ask them in the Q&A section. And Pierre, Karim, and I will be glad to answer you. So thank you for listening to me. It's time to give the floor to David. So maybe Pierre, you can present David.
Yes. Thank you, Marie. So David is a part of the dream team, of course, as I said before. And we can maybe go back in the past a bit. So David was involved in the first big school in 2016, kind of the ancestor of the Gray-Scott School. So was one of the teacher at this school, and in fact he's a real teacher. He do a lot of teaching in his time, so it's natural to have him on the school. And it started also in 2016, the Reprise project, which bring you practically all the teachers we have in the school. So it's an important part. And of course, without David, we cannot have this school. So David, I give you the floor. And if you want to add something, feel free.
So thanks for the nice introduction. Today's webinar will be about Sycl. And so I will start my story actually with OpenCL. So back to 2008. Where the aim, which is also now the aim of Sycl, was to try to be as portable as possible for acceleration hardware, and so how to be able to make some code that would run on CPU, GPU, FPGA, etc. So that was the goal. Did we reach it? More or less, but I will start showing you an example of codes, so to see how far we have evolved today. So at the very beginning, the idea was to work in C, so to support kind of any hardware. So for example, we have this include, and the kernel code, the code which is doing the computing, were given as a text actually in the code. So that's why you have all those \n, etc., and the quotes. So not something very easy to write and very readable, and also you need those magic words such as __ kernel, global, etc. And that's the main. So I just want to take a collection of numbers and make the square of them, okay? So I need all this boilerplate code. I must declare number for error, the platform, the device, the context, the command queue. There I'm taking the program from the source I showed you before. I will create a kernel and will ask the program to be compiled. I think it's, yes, there we have the CL build program. I must create buffers to exchange the data between the accelerator and the host machine. And then I will need to queue my kernel. Also, for each data, and I must exchange between the host and the accelerator. I must do this call of the set kernel arg parameter by parameter. For each parameter, I will need to make a call. Then I'm unqueuing the kernel, trying it to finish, get back the results, finally release anything. So to do something such as a very simple square, I will need all these instructions. So that was the price to pay to be in C and to be able to support any kind of hardware as much as possible. So obviously it was quite fast, not doable by humans. And we got in 2013 this what I call the rise to C++. So Sycl the aim is to take the same ID. I want something able to run anywhere, but they made the choice of the C++ language, so to be able to do things more easy to write and read as a developer. So let's see the same example as before, but I just need one slide instead of the 3 or 4 slides as before. So how to make my code run on Sycl? I will first create a queue. In this example, no arguments, so that is the default queue, which will choose for you the default device on your machine. If there's a GPU, it will generate select the GPU. Of course, you can select better, but we'll see this after. So I'm creating my queue. I'm creating 2 buffers for the input and output. I submit my kernel. So the key point is in the Sycl is that we are just using usual C++, no specific construct or no specific keyword. So usual keywords, but this highly rely. You are not obliged. It's not mandatory, but the easy way is to use lambda functions. So as I will said at the end, to follow this course during the school, you must have practiced at least a little the C++ lambda function, because we use them quite everywhere. So there I'm submitting this lambda function, which describe a task, because the organization of Sycl program is a set of tasks coming one after the other. And at the first level, lambda level there, I'm describing a task, and I define some accessors, which is the way to use the buffers I made globally before. Defining the accessor is an opportunity to say it's read-only, write-only, or read-write by default. And with this information, the scheduler of Sycl will organize my task automatically for me. So that's probably one of the easier way on if you start a Sycl program is to use buffer and accessors, so that the organization of the task will be done for you. And then at this level, with the parallel for command, that's where I'm defining the kernel to run in this task. Again, I have an embedded lambda, and finally, just the code I want, the output equal the square value of the input, and that's all. I also need a wait, because when you submit in Sycl, when you submit a task, it is an asynchronous submission. So you can submit many ones. Thanks to the buffer and accessors, the system, the scheduler will organize which kernel must be run when. And finally, the host code is going on because it's just asynchronous submission, and at least I must wait once to get for the result to be done. So that's the modern Sycl way as compared to the OpenCL we've seen before. And I will describe you more details about each of these steps and see a very small subset of the many things we can do with Sycl. That's the default, but of course we can control if we need. I also would like to add that my example are in Sycl 2020, even if Sycl has beginning in 28. But for the demonstration, for the webinar, I prefer to use modern Sycl. So first, the selector. So you've seen Q there will select what they call the best device, which is something very subjective. But there are a default selector, the second one there, which is just going through available devices one by one, give them a rank, and the one with the better rank will be selected. You can be more precise and ask, I want a CPU, or I want a GPU, or I want FPGA, etc. And you can write your own selector, which is given again as a lambda there. And this function will receive the device one by one, can analyze many properties and give a rank so that the system, the Sycl runtime, will select the better one. A key point here is that the philosophy of Sycl is that you have your code and you should be able to run it anywhere, not necessarily knowing in advance what is the available hardware where you run your program. So there is this discovery mechanism so that your program is querying what is the available hardware, choosing the best one in your definition of what is best, and also it will compile on the fly the kernel so that it can be run on the available accelerator. So I've shown you before a very, very simple parallel for, which were making the hypothesis that your computation is embarrassingly parallel, but sometimes you need to get more control. So for example, there, I'm showing you that you can explicitly give an RD, an ND range, where you give the global size of your problem and the subsize of the subgroup that you will use. And on GPU, it can make sense that you choose a subsize which is the right one for this CUDA hardware or this AMD hardware, etc. So if you need, you can have more control, and also you will explicitly need this ND range if you want to access things like as the local memory of the subset of computing items you are addressing. So quite fast in general, in a real problem, and specifically in Grayscale 1, we will need this kind of parallel for. So at the beginning, I have used the buffer on accessors, which is the recommended way to work if you start a new program. But sometimes you start from an existing legacy code, and it may be more simple to use another way to manage the data based on pointers. So this has been added in Sycl 2020. And for example, you may do, instead of any new command, you may do a malloc shared as demonstrated there. And the key point about the malloc shared is that the data which is in this memory area can be accessed both on the host and on the device. And you don't have to care about moving the data because the Sycl runtime will do it for you if the device has this property. But generally it's the case, at least for GPU. And so it is the job of the Sycl, the runtime, to move the data, for example, from host to the device if you are starting to run a kernel which is needing this data. And so you don't care about moving the data explicitly. That can be a good starting point with a reasonable performance. Sometimes you want to go better, specifically if you want to make some overlap between the I/O and the computing. And so in this case, better not to use the shared memory, what is called the unified shared memory in Sycl, but rather to explicitly allocate memory on the device, and then do explicitly the copy yourself. So there, I'm doing the mem copy from the input host. I make the hypothesis I have an input array, classical vector or array in my host, and I'm asking to copy this on the device input, which is the memory I just allocated on the device. And this, as the action on the computing kernel, is an action that I submit to my queue. Each time it's asynchronous, so you see that each time I'm also adding a call to wait to be sure that the data is here before I am running my square, and I wait then for it to be finished and do the copy back. So that's the way you make everything explicit. You have the more control. You may have, in a complex example, that's the way you may have the better performance. But there is more work to do for you. A way to avoid the wait there, if I have very simple computation, I can declare my queue to be in order. And in such a case, every time I submit a new action to my queue, it will be put in the queue and they will be run one after the other, waiting each time automatically. I just need the final wait so that my host code is waiting for the queue to finish, but I do not need anymore the intermediary wait as before. But this, of course, will only work if I have a quite simple graph task. On the contrary, if I have something very complex for what concerns the dependencies, I can get each time I submit a command, such as make an action, such as memcopy, submit this parallel for, etc. I am return an event which is able to say, is it finished or not? And each time I submit a new thing, I can say that my current task is depending on a given event. And with this mechanism, I can do very complex graphs of tasks with complex dependencies, all under my control, so that the runtime Sycl can absolutely optimize everything. That's a way to describe the graph of tasks, saying which tasks come after which other ones. Sometimes it's easier to describe your task, your graph, as a graph of data, saying which task depend on which data produced by which other task. And so in this way, I'm back to my initial way to describe things, where it's easier to define these buffers on access with the accessors, saying each time it's read-only, write-only, or read-write. And this way, the runtime will do for you the dependencies with the event, etc. So that's a view with the data flow. But if you prefer, as before, managing yourself the events, you can have a view which is a flow of tasks, depend on your problem. So that's all I will show to you about the Sycl. For more technical details, let's meet at the school in July. But I want to discuss a little about what is happening behind the scene. As I shown before, anything is done so that when you write your Sycl code, things are more or less simple, but easy to manage and uniform, portable, etc. That has a price. It means actually more work for the guys which are doing the installation, compilation behind the scenes. So let's have some look a little to it. And before some history. So the initial proposal for Sycl came in 2013 from a company called Coldplay. That was the proposal. The actual first certification standardization made by the Kronos group came in 2015. That was Sycl 1.2. Then Intel integrated support for their FPGA hardware. That was a big date because I do not think of other portability layer which can manage both CPU, GPU, FPGA. And we got in 2016 Sycl 2.2, which is moving from C++ 11 to C++ 14, and also with OpenCL 2.2 as a backend. Then we have the Xilinx which announced support for their FPGA hardware. And finally, the last big date, I would say, is 2020, when we got the Sycl 2020 standard that we use today. What's happened in the industry, a big date also was 2022, when Intel acquired CodePlay and start to develop and contribute much to Sycl, and with their implementation called DPC++, and adding from time to time support for C++ 17, especially OpenCL3, etc. New types, backends, and we have now continuous evolution of the support. This slide, this graphic is rather old, but just to show you, when I say old, 2020 perhaps, to show you that we have many implementation of Sycl available. The main one, I would say, the leader is DPC++ from Intel. And also at that time, we still had CodePlay, which were implementing Compute CPP, but today both have merged to provide an even better DPC++. The outsider, which is interesting also, is Adaptive CPP, which is developed by a university, the University of Heidelberg. And you have also many other ones. I'm not sure the situation today, but each company doing its own hardware will try to support Sycl so that their hardware is easily usable in an application doing HPC. What I should say, perhaps, if you are looking to Adaptive CPP, is that the name has changed quite often. So at the very beginning, it was called IP, perhaps, I'm not sure. Then it was renamed Open CPP, which was too much for other partners, I guess. So finally, they named it Adaptive CPP, which is the name for a while. So that's the second, I would say, the second interesting implementation of Sycl to follow. As you can see also in the graph, actually, you have Sycl, but Sycl will delegate the execution to a lower level standard or intermediary layer. We add OpenCL at the very beginning, but now you can have other backends, especially Intel is working with this level 0 layer, which is the abstract layer for all the hardware. You can directly address also CUDA hardware now. I'm not sure what is the backend. We have several ones, but you can see that OpenCL is already there, or an equivalent, which is the backend hardware abstraction. A big point about Sycl 2020 that I want to emphasize, that this one has opened the door to have a CUDA backend. So that's the point where the Sycl was able to handle also the NVIDIA hardware. I think it's CodePlay which has done this backend especially. About the compilation execution model, I just took this from an Intel book, I think, but the idea, especially with DPC++, is that the initial philosophy, as I said, was that the Sycl runtime is discovering on the fly what hardware is available, where you run, and will compile just in time the kernel you want to run. But of course, if you know in advance which hardware you want to target, there's possibilities to pre-compile the kernel for this hardware, and the corresponding code will be stored with the application and made available. You have also all these intermediate representations which can be done in advance, so to speed up the runtime when starting on the real hardware. So one can mix with, at least with DPC++ implementation, one can mix ahead of time compilation, just in time, depending on the need. So now I would like to talk also about one API, because a Sycl is one thing, which is, I would say, an alternative to CUDA. But CUDA, it's also a big ecosystem with many libraries. for typical applications. And so Intel tried to make some kind of equivalent ecosystem on top of Sycl, and they called it One API. The basic idea, I think, started in 2018. And the first release of what they call the base toolkit was in 2019. And then we got all those evolution. In 2022, the support for ARM on RISC. In 2020, the level 0 API, which is a replacement for Intel hardware, or replacement for OpenCL, the support for NVIDIA and AMD, etc. At the moment, Intel chose to, from the beginning, all that was open source, I think, and available. And very recently, last year, end of 2023, One API, Intel gave One API specification to a new foundation called the Unified Acceleration Foundation, which is under the control of the Linux Foundation. So that's the moment where they put everything under governance of the community, the open source community. Even if Intel stayed the main implementer today, but that's open, that's available. And when I was looking for news, and I would say that the biggest news, I think, last year linked to this new IJCL foundation is that some European project choose to port Sycl on One API to RISC-V, and they made it because they, as you all know, they tried to provide a European processor, and they want to support it and to program it through Sycl on a One API. Also, recent news was the revision 4 on One API, which has transformed the mathematical library into one math today and extending One DPL. And I will say you a little more information about One DPL. So what's the ecosystem of One API? We have this level 0, which is the abstract layer, the hardware layer interface abstraction, able also to be used to connect Intel CPU, Intel GPU, Intel FPGA. Then you have DPC++, which is the Intel implementation of Sycl. I'm not sure this is DPC++ is part of One API, but that's the Sycl implementation. You must know also about this Syclomatic tool, which is a way to transform a CUDA code to help you migrate your code from CUDA to Sycl, which is not something very difficult because same problem, same solutions, we just have change in syntax. And of course, since CUDA has a longer life, you have many modern features in CUDA which perhaps don't have an equivalent in Sycl, but most of it can be migrated. And then One API in itself, you first have One DPL, which is basically the low-level algorithms, a kind of refactoring of what was called before parallel STL. So taking the algorithm from, looking like the algorithm from the standard C++ library, but making them able to run on any accelerator hardware thanks to Sycl. And so all those are the one for the math, one for the machine learning, video, thread, etc. One TBB, which is a renaming of the former TBB, already very used, at least in my energy physics community. And I would like to show you an example of the use of One DPL, because if I want to compare Sycl to something like Kokkos, for example, I should add One DPL level to be at the same level of service. And so you remember perhaps, so that was my initial square example with Sycl. So the queue, the buffers to discuss with my original arrays from C++ program, submission of my task, defining the accessors, and then finally starting the parallel for asking to square the input. So what if I have one DPL and I want to do the same? Actually, it's a lot more simple as expected. So there's some change in the includes, but there, the only things I need to know actually is to make a very specific policy. You have seen before with talks from Pierre, I think that STD transform, for example, in C++, now has a policy as first element, which is saying I want to run it in parallel or I want to vectorize or other things which are equivalent. And just the same, if you use one DPL, they have generalized the concept so that you can put new policies. And these new policies will drive actually the connection with Sycl. So there it's very simple because I'm using all the defaults. I'm even using this execution DPCPP default policy provided by one DPL. And what is doing this policy? Actually, when I create the object, many things happens. The creation of the policy will trigger the creation of a queue. It will trigger also the call to transform there will recognize the input and output as a typical arrays. And the specific implementation of transform, which is provided by one DPL, it will create buffers on the fly. It will create accessors for you. And we finally take this lambda and submit it to the queue. All of this automatically. So you just define this policy and you will get the default queue, the default buffers, and anything running on your default accelerator. Of course, you can take the control and you can build yourself another kind of policy when you will do a specific queue, selecting the hardware you prefer, change the buffers characteristic, etc. If you need control, you can, but the basic idea is that you use the usual algorithm, just like you used them before in the standard C++ library, and just change the policy. Of course, it only works if you can express your problem as a sequence of such transformation of algorithm, but quite often it's not so simple, so you will get back to coding Sycl yourself. But for basic problems, we have working basic solution. And one DPL will do the work for you to connect your algorithm to whatever hardware you have. That's the magic of it. Oh, I'm already to the conclusion. I'm going too fast. I hope there will be questions, or I will don't use more than the time expected, but I can develop a little. About some conclusion, which, as I said, are very, very personal, subjective, questionable, so don't hesitate if you want to question. So, what I call bitter sweet news. We have a lot less boilerplate code in the user code as we were expecting as compared to OpenCL from the beginning. We can be, especially you have seen until with one DPL, we can be a lot shorter when writing the code. It is very nice. That has a price which is more complex installation work. Compilation chain, execution, runtime, etc. The complexity is still there. So what you don't have in the user code, you will have it in the backend. But that's nice because at least in my domain, I work with much physicists. They are doing the easier work to do the user code, and some engineers will do the backend work, which is more complex. But that's fine. As compared to CUDA, for example, debugging and profiling will be more difficult. So the first thing you must do if you want to debug your code actually, and which is easy to do with Sycl, is to say, okay, I will first run on my CPU, because the beauty of the thing with Sycl is that it's not GPU only. If you have no GPU where you run, you can run it on CPU, and we'll try to make it performant as far as possible. And also, it's a nice way to debug running on CPU before you move to the GPU accelerator. When you move to the GPU, most often you will try and need to debug and profile with the specific NVIDIA or AMD tools. And then the result will not be exactly what you have in your initial user code. So you have to mentally make the connection. Can prove painful. So I will not lie to you. The debugging profiling tool in the Sycl world, of course, are not as good, especially if you are using a CUDA accelerator. The debugging profiling tool will not be as good as the CUDA ones from NVIDIA. But that's a price to pay to have something more portable. Now some real good news, I think. So we really have more and more hardware addressed by one Sycl implementation or the other. So that's the good part of it. That was the initial aim. Especially, I hope one day we have these European processors, and we will be able to run Sycl on them. We have Intel fully involved for years in the ecosystem, developing one API, and finally giving one API to the new foundations. So with this ecosystem of libraries, we reduce the gap with the CUDA ecosystem, even if CUDA is still evolving, improving. So that's kind of race, but we have some libraries to do advanced things. For people which wonder, is it worth to port to Sycl? But this is true also for porting to Kokkos or porting to whatever portability layer, even porting to CUDA. Even if afterwards you don't use accelerators, actually it forces you to make your code better. So don't worry to choose the good solution, the good portability layer, which will be the winner in few years. Whatever you choose, the porting of your code will make it better, even when running on the CPU. So that's worse, if you wonder. And also, from what I see about all the solutions, is that until now, at least, they converge. Because Kokkos and Alpaca, for example, they want to support the Intel GPU. They are making a Sycl backend, which is kind of strange because I think also Sycl could be the front end, but at least to get the access to Intel GPUs, they make a connector to Sycl. So we have several portabilities layers connecting one to the other. I also noticed that adaptive CPP has now support for C++ parallel execution strategy, the same as 1DPL trying to provide some solution to run the C++ classical algorithm with GPU backends. I noticed also that Kokkos includes what is the reference implementation of the new MDSpan in the C++ standard. So all these people take inspiration in the solution of the others. They all contribute to the evolution of the C++ standard. They imitate what is good from the others. So all those solutions, more or less, I think, are evolving and converging with a common things, which may be not already C++ 26, but perhaps 29, I don't know, but they all go the same way. So if you start to master one of the solutions, it's quite easy to move to the other and to see how it looks like. Now a few words about what we will do during 2025, this session of Grace Code during the school. So about the prerequisite, I recommend that you know what is a C++ lambda function. Of course, you should try to, if you want to use your own machine to set up Sycl on it, we will try to give you instruction later on to how to do it, how to use it. There are easy solutions. For example, Intel is distributing Docker images where quite everything is installed, but there are big images. So if you want to use that, you should pull them before coming to the school, or you will kill the network. You will have also already things set up for you in the satellite sites. You may use code recons, as said there, which will provide some accounts where everything is installed. So think in advance in your Sycl setup and work with C++ Lambda if you never did. And that's okay for the prerequisite. During the school, we will mostly do practice, not so much theory. The idea is to try to make a port of Grayscott program with Sycl. So during the first week, we'll mostly work on, not mostly, uniquely work on CPU, trying to have some automatic multi-threading and possibly vectorization, I hope. Not so easy, because there we have a fight between Sycl and sometimes the auto-vectorization features of the underlying compilers. I fear it's not so easy to get the vectorization, but we'll see if we have some progress on this. And the second win, we will move the code to GPU, and most of the work will be optimizing data transfer, because when running on GPU, you already know probably that a key point is that we need to move the data from the host to the GPU memory. And if you don't organize this well, the time you gain running on GPU may be wasted transferring the data. And especially at the end of the session, we'll try to overlap both the exchange of data with the computing. So I said many things on which platform you will be able to run. You will be able to run on Code Recon, which is a partner of the school, Must, which is the ANSI Meso Center. You can also choose to run on the Intel Dev Cloud, where you just make an account. You can do it try it in advance, and you will access a virtual machine where everything is ready. You can get the Docker image we will prepare, or you can even use the resource of satellite site. There, I'm giving you many links, my preferred ones. There's no such things such as the CPP reference for DPC++ and Sycl. So I think one of the best resources is this book, which I gave the link there. Beware that there's 2 editions, so take the second one, which talk about Sycl 2020. You have the links in the slides. I will have to share the slides one way or another. Have a look at Adaptive CPP, which is the alternative the main alternative implementation. You have the Chrono standard. What they call a reference guide is rather a cheat, resuming anything available. And as I said, the documentation is one of the difficult the thing which can be improved in Sycl, because you either have the specification how to read, or the cheat, which is a very short resume of anything available, and almost nothing in between. So generally, when people want documentation, we send them to the book, which is referenced there. This book is free, available online, etc. So that's really a good reference. Sycl Academy is something producing some courses, short courses you can practice. I put you the link to IOWCL workshop, which I think is the main workshop about OpenCL and Sycl, which generally take place in Europe. And finally, a link to the UXL Foundation, which is now managing the OneAPI specification. And then you have all the main links about this. I think I will use given the horror, I will also use my backup slide. A few words about what we do in high energy physics. Whatever I said before, I would say that today, at least in our domain, people have not chosen a unique solution yet about how to do the portable parallelization solution. Why so? There, it's comparison of the implementation of various portability layers. So I would say 5 years ago, Sycl, HIP, directives with OpenMP. There's also OpenACC, Alpaca, and the new execution policies for the standard C++ library. So you see there that we can get it with NVC++ on NVIDIA, and one API DPL is the equivalent if you want to use the standard C++ algorithm in the Sycl world. I can say a few words about this. Basically, I see Alpaca as something which is able to address both CUDA, NVIDIA hardware, and AMD hardware, mainly. Kokkos is more general, and the directives, I don't care. We made some tests, and as you see there, the result was not so good 2 years ago. I don't know a recent study which made the same, but we see that at least at the beginning there, the performance on this problem, which is a very specific one, P2R, on some of our problems in high energy physics, Sycl was not performing good. That's why we have not yet adopted for anything. But we have some good experiments, good experience. For example, in this recent conference for energy physics, we see that Sycl was tried to do some Lorentz vector algebra with good performance. I have much other citation. We use it for MATgraph with good portability and performance. That are tools that were given in last year, IJCLab. Good performance also with what we call columnar data. I will let you look the details if you want on the slide later on. So that's my backup slide. So back to my conclusions, and also back to what we will do in the school. So first week, CPU, multi-threading, vectorization. Second week, GPU, focusing on data transfer. And that's all for me today. So if you have questions, I'm okay.
Okay, thank you, David. We have plenty of questions.
Oh my God.
Yeah, but we have time, so it's not a problem.
Yeah.
So from John, is Sycl a strictly single node thing?
Yeah. So I don't heard about things handling multi-node or multi-site things. But I would say yes. I'm sure if we search in detail, we'll find some tries to make it multi-node, but basically it's single node. The aim is to be able to handle any accelerator on your node.
In fact, it depends on what the interface of the backend can allow the backend to do. So maybe it's not that simple, but okay. Second question from Jan. Does Sycl support the functionalities of NVIDIA AMD math libraries like QTensor, HyperTensor, stuff like that? Maybe not yet.
I would be surprised.
Yeah, or maybe with the ++26 with the new interface coming.
Oh yeah.
At some point, but not today.
No, not today.
Okay.
Of course, the very last nice features of CUDA and the specific hardware of CUDA is not taken into account in the general specification. So we are more portable, but we are less able to use the very last improvement in this or this hardware.
Now, maybe a question about that. Do you know if you can use the tensor cores with Sycls or not?
I don't.
Because here you are using the CUDA cores or the classic computing cores of the GPU, but can you use the specific hardware for the matrix multiplication?
I will take this question on a paper for the school.
Okay, thank you.
Because I think
I'm very curious about that.
Yeah, it's a very good question. I fear not, but who knows? CodePlay is working intensively, I think, for the connection of CUDA hardware in Sycl. So of course, using the tensor core is something important, but I've not read anything about this, but I must investigate because I think it's an important point. So we will try to answer this in July.
Okay. So a third question from Jan. Does Sycl runtime take data locally into account when distributing tasks? In your tensor operation, display a big role, needs to be part of any cost function deciding on task distribution.
As you will discover, my personal focus is to have something very portable. So I'm not very aware of the detailed specification or use of this or this hardware. My main, I would say my main goal personally is to have something able to run both on GPU and CPU. And that's already big stuff. So yeah, that's I think that's the secret of the implementation. So I'm not sure if the Sycl implementation of Intel is doing good data locality or not. That's something that must be tried. I'm looking at the answer of Adrian.
It depends on the backend, in fact.
Yeah.
But as you said before, if the backend is not going to do job for you, you can change the backend and normally should be okay. So it's not a problem.
That's the interesting point. But sometimes it's quite secret or hidden or difficult to know what is doing the backend.
Okay, question from Tom. Question for the summer school. I found that it's a good idea to show the prerequisites of the courses. Do you plan to do the same for the other one for the school? Yes, it's definitely a good idea, so we will do it. So for the next coming webinars, yeah. Question.
I see an interesting question from Rodolphe. Want to know about the support for Apple silicon hardware. I'm not sure I've ever seen the name of Apple in the people supporting Sycl. So you see, you have Intel very involved. You have CodePlay doing the connection to CUDA hardware for them. You have all the manufacturers which are doing their specific hardware, trying to make them compatible with Sycl. I'm afraid that Apple prefer to live in the Apple world and do not care. But
that's possible.
But it would be fine because more have now Apple workstation with these new ARM processors. So I will keep the question also for July to make an investigation about this because I think it's a very good question and important one. I'm not sure Apple would like to be supported by Sycl. So. For example, before NVIDIA was doing the minimum with OpenCL, just doing the support for OpenCL, very old release, not putting effort in migrating to the new Sycl 2020. Now it works with CUDA because CodePlay needed to do it, and CodePlay needed to do it because I think there is one of the big supercomputers in the USA that were mixing. CUDA graphic cards with Intel CPU or something like that, and it was needed to have something Sycl supporting CUDA. So they made the effort. But for Apple, I'm not sure.
Question from Biagio. There is a nice Sycl extension for cluster of GPU called Celerity. So if you want to have a look, normally for that. Another from Biagio, Intel has an extension called Sycl John Matrix extension, not in the standard as Intel extension. Okay, so you can use that also if you want. Okay, there's a tensor core. So again, from Biagio, the tensor core seems to be mapped on the NVIDIA backend. So again, a problem of backend, but that's fair. If you use a backend for NVIDIA, if you can use the full NVIDIA, it's nice.
One thing that we may try to do if you come to the school is that generally I'm proposing around the Grayscott application some kind of benchmark and asking people who wants to try to, on their own hardware, to run it and make it work and compare, and perhaps because in the room generally we have expert of CUDA, expert of NVIDIA, expert of AMD, expert of this or this. and it's interesting to have anybody trying to run the same code and see how it performs.
Yeah. A question from Frédéric. How does Sycl compare to OpenSCC?
Oh, that's the fight between the directive approach and the embedded language approach. Personally, I'm practicing C++ any day, and I prefer a solution which is C++, and just a way to use. But I like directives. I would recommend directive as a first step when you are trying moving from a sequential code to something more parallel. That's an easy way to add some decoration in your code to get it parallelized. But at the moment, I think you're too limited. And if you make something a little in real life, at the moment, you need to have more control on what is going on. And I think today, at least, it's even if one DPL is very simple to use, or the new C++ policies in general are very easy to use and nice, you have a limited access to what you can control, and it's good for simple problems, but at the moment you need to put your hands within and control more what you are doing. So I think I know a colleague also. I think Vincent. I'm not sure it is in line. I don't think so. But Vincent, which will be at the school, has made some OpenSCC on quite complex problems. So apparently, he's successful in using directives to do this. But myself, I prefer to have more control and have the full language available.
So there is no more question in the chat or in the Q&A, so I will move to my question because I have a lot of questions also. So if you have other idea for the question, don't hesitate, but I will switch to mine for a moment. So yeah, at the very beginning, you present the queue to select your device.
Yeah.
You need to have a precise idea of what is the computing needed for the program to choose the best device.
Yeah.
So it's again for the design of your application, it's important to have that in mind. So you cannot improvise. Okay, I select that design, that device, and then I don't know what I do with that. So it's a good point.
So your question was, can I control more precisely my queue?
Yeah, I know we present that, but moreover, on terms of the design, you need to be aware of what should be your needs in terms of computing before you create your queue, in fact.
Yeah.
To be sure that you will select properly your device.
Yeah.
So in terms of design, it's important to have that in mind also.
What I've shown about the queue is the very beginning, but you can make your own selector. And when doing your own selector, you have access to many information on the device. The list of properties you can query about the available device is quite detailed. And you can even do things like tell me what is the optimal subgroup of computing items in the hardware, so that when you are doing your range, you select the good size, etc. for advanced use.
And speaking of range, for your parallel 4 example, if your buffer size is not a multiple of your size...
Oh, I have no idea.
That's a good question also.
Yeah, I put it in the question.
Yeah.
Do
you have a problem or not?
Yeah, I don't remember if it is mandatory to have size a multiple of subsize.
Yeah, I don't remember too. So.
I think it's not so mature, so that everything is running automatically on working file.
Okay.
I think you still need to look at the details to have something efficient if you want so.
So I have a question also about the malloc shared.
Yeah.
So there is an heuristic, and you can automatically move data from your device on your host. But is there some moment that you prefer to do your transfer by hand or not?
Yeah.
Speaking of the amount of data you want to transfer. Do you have clues about that?
We made a paper. I don't have the reference anymore, but with PhD working with us, we made a comparison between because you see, you have the choice. You have many choices for what concerns the transfer of data. Either you define your program with the buffers and accessors, just saying who read, who write, and it will decide for you when to move the data. That's the data flow view. But you can explicitly rather define a task, a graph of tasks, and either use this implicit move of data or explicitly move it. And we observed that as expected, if you know your problem, and you know when it's better to move the data, and if you do it explicitly, you can be a little more performant than if not.
Yeah, so you have to play with that as for CUDA, as for NVC++. You have to play with that.
After that, yeah, but I would add that when you know your problem and you make hypotheses on the hardware, you're better. But if your code, you will run it on any kind of hardware, GPU, CPU, etc., perhaps the implicit system will have a better performance in general.
Yeah.
Because when you optimize for a given hardware, thinking I need to move the data, the size of the memory is that in my accelerator, etc., you have in mind some hypotheses that will work on this example, but will not work anymore if you use a new hardware. So,
okay, speaking of hardware, again, also malloc shared, if you are using the CPU, do you have a copy or a kind of a transfer, or is it completely transparent and you have only one pointer?
To be checked. I hope not.
In fact, for me, it's a matter of optimization for the backend. But the problem with that is if you debug on the CPU and then you debug on the GPU, you don't have quite exactly the same behavior.
Sure.
So it's important to have that in mind also.
The way is first you debug running almost even sequentially to be sure that you have something. Then you introduce parallelism step by step. So first running on CPU is good to debug a subset of the problems, but you will not see anything, everything, I mean. So finally you move to the GPU, and there probably you will have new bugs, which will be harder to solve, but it's always good to start running with the CPU backend because you will see a subset of the problems and keep only the specific one for the GPU afterwards.
Okay, about your Lambda, can you synchronize threads inside your Lambda as we can do in CUDA, for example, all this fancy stuff, or is it too specific?
Synchronize between the computing items? Yes,
yeah.
I'm not an expert on this, but I've seen, there you have some instruction called barrier, fence, etc.
Okay, so you can,
yeah, within subgroups, etc. You can do this kind of stuff, and you need to quite often. So
yeah, and speaking about profiling and debugging, because you mentioned that you can have task graph and you can do a lot of stuff with that. So you have to find a way to debug. But I don't get, if you are using, for example, the CUDA backend, normally you should be able to use all the inside stuff and profiling stuff from NVIDIA. So normally, I don't know why you are saying that it's worth.
I was said by people doing this that the limit is that the CUDA tool will speak to you the CUDA language. So sometimes you have to translate what is said in the Sycl word to understand what it is saying about what. But
but for me it's a problem of backend because now you have NVTX, so you can specify in the NVTX session, okay, I'm doing this kind of Sycl stuff. So for me, it's not.
You think it's but okay? We'll practice.
For me, it should not be a problem anymore because it's it's not portable, but it's okay, Adrien, but it's a matter of backend. So if I'm using a CUDA backend, I want
and we
I want to be able to use CUDA tools. It's normal. If I use Intel backend, debugging. I want to be able to use Intel tools. It's normal also. So there is no problem with that. Okay, Sycl is ahead of time of just in time. It depends on the backend. But if you want to to provide your program to many people, and you want probably to avoid to have a compiler inside the container you want to deliver or the software you want to deliver. Is it possible to compile everything ahead of time with several backends to say, okay, I'm sure I will target, I don't know, NVIDIA and Intel, so I compile ahead of time for only NVIDIA and Intel, and is capable to switch automatically? Is it possible or not? Or maybe it will come at some point?
From what I understood, you can mix. So you can pre-compile for some hardware because you know it's a possibility and you want to have less latency when running and starting fast, and still keeping the possibility to compile on the fly if you need to. So
yeah, that's really powerful.
But I fear one thing whatsoever is that probably when compiling, you need to specify which kind of intermediary representation you want to have.
Perhaps, if you want sphere V, if you want those stuff. It's normal.
And probably if you don't put the right list, some hardware at runtime will not be supported because you don't have the intermediary representation needed, this kind of stuff.
And Adrien said also in the chat, you can also cache the JITed binary and try to use it in the next application. Or yeah, it's totally possible also. Oh yeah, a question about 1DPL. So do you have to use explicitly DPC++ to compile it as we need for NVC++, for example, or is it okay with G++ or Clang or stuff like that?
I'm quite a beginner with 1DPL.
Okay, or maybe it's simpler to compile with DPC++, but you can with other.
I think you need probably. I will note it, but I think you because last year we did not made anything in 1DPL, but I plan to use it this year. Okay. Also to have the comparison with NVC++, Kokkos or whatsoever. So I won't try this year. It will be the new thing in this year session to try also Grayscott with 1DPL. And I suspect that you need the specific compiler because I think even if when we call it, you call STD transform, I think the implementation of this STD transform comes from 1DPL, and probably you need the specific compiler to get the specific library, putting this implementation, able to recognize the specific policy, etc.
Yeah, okay.
But I'm not 100% sure, so to be checked. Because, the aim of giving one API to this new foundation is to make it independent of the implementation. So,
in fact, if you are using STD transform with TBB, you have to link to TBB, but you don't need to use DPC++. You can use G++, Clang, NVC++, whatever you want. But you have to link explicitly. Maybe the compiler will hide this for you, but normally should be quite feasible. Not really easy, but normally quite feasible. Oh yeah, can you combine 1DPL with classic Sycl stuff?
Probably, yeah.
Because it's Sycl talking to Sycl, even if it's not the same layer, normally should be.
I think the implementation of 1DPL is using Sycl, so it can be mixed. Especially as I saw you. Yes, I'm even sure because I show you the most smaller example possible, just using the default policy. But when you're creating a policy for STD transform, you can construct this policy from an existing queue.
Okay.
And also, if you have existing buffers, you can call specific function which will create iterators from those buffers that you can give as begin-end to the transform algorithm. So actually the answer is yes.
Okay, so you will speak also at the school for both CPU, GPU computing at the same time? With I don't know with the balancing or not, maybe it's not that simple.
No, it's you which will do the work, I fear. Actually, if you want to use both at the same time, you are doing a queue for the CPU device, for the CPU seen as a device, another queue for the GPU, and it's your work to send some task on one queue, some of the tasks to the other queue. So choosing what will go on the CPU, what will go on the GPU. I don't know about the runtime of Sycl being able to choose the accelerator at runtime, depending on some runtime context. You are the one which must do the work in this case. Yeah. But you can cross things. For example, you can make some task action on the CPU queue, get the events, and make some GPU action depending on the events from the first queue, etc. So you can make cross dependencies between the queues. But load balancing, I think it's stay your job as a developer.
Yeah, you have to know what you are doing and what is computing needed. Okay. Yeah, last point for everyone. If you want to get the Intel image, Intel containers to do Sycl, normally it's something like 15 gigabytes. So you have to prepare yourself and to have space on your disk and not to kill your internet. So yeah, it's really heavy. Yeah, you have everything in it, but it's really heavy, so you have to take care of it.
Intel has not made this work to have many images with small parts depending one on another. You take the big one or not.
Yeah, for NVIDIA it's the same. It's not 15 gigabytes, it's something like 5-6 gigabytes, but it's a lot. So yeah, you have to be aware of that. And yeah, I think also you have in your lecture, if you want to use the Intel container with the CUDA plugin, it's also even bigger, something like that. I don't remember.
Potentially, yes.
Yeah, it's a bit bigger because you have all the CUDA stuff behind it and all the NVIDIA stuff. So yeah, it could be really big. So
it's quite easy to install and it's quite surprising. But Codeplay, they made a good job. And when you have the Intel ecosystem and you want to add the CUDA. In my experience, at least, when you add the CUDA backend, it's just one line, one instruction, and in few seconds later, the connection with CUDA is done. So but you must pre-install CUDA before. So you must have all the Intel ecosystem, install CUDA, and then the glue, which is done by Codeplay, is very fast to install and working.
In fact, installing DPC++ in bare metal is really simple. So you go to the Intel website, you get your DPC++, it's one line, you start your bash command, and that's it. So it's really nice also to have that. Okay, so if there is no more question, I have one last question, and we will be able to finish on time. Why JavaScript?
On the slide,
yeah.
Good question. Why? Because that's what I got when I got the model for my slides. But I promise for next year. I tried, but this year, but I prefer to focus on one DPL new slide in my presentation. But I promise next year the backend of my slide it will be Sycl code.
Okay, so
and not JavaScript.
It's one DPL or a new backend, a new background for your slide, not both at the same time. It's too much work. Okay.
Yeah. I asked to ChatGPT to make a new background image with Sycl code, but was not nice.
So yeah, we have a lot of thanks. Okay. That's definitely the time to stop. So thank you everyone for attending this webinar. Thank you, David, for the presentation. And see you next week for Fortran and CPU and GPU. Have a good day and goodbye.